My name is Brent Fritz, and I am project lead for Titan Rover. Titan Rover comes from California State University, Fullerton. We are comprised of 25 multidisciplinary members, including mechanicals, electricals, computer science, computer engineering, business, and geologists. And this is our submission for the URC 2016 presentation task. Titan Rover is structured under a top-down hierarchical system. The project lead delegates tasks to the system team leads: mechanical, electrical, software, science, and business. The project lead and sub-team leads meet before general meetings to ensure cohesive actions and understand priorities. Under each system lead are a system of sub-teams. This ensures each component of the Rover system has a person or persons directly responsible for quality and completion. Together, under the system lead, they work to ensure effective communication between all of the Rover systems. The mechanical team is largest in membership. This is due to the requirements of each mechanical student to undergo a year-long senior design project, and we have had many eager members at the beginning of spring. The project lead comes formally from a mechanical background. His direct responsibilities are chief delegator in ensuring a cohesive Rover system of parts. All parts must be reviewed under either the project lead or mechanical lead prior to manufacturing. Under him are the sub-teams of suspension, wheels, and chassis. The robotic arm requires a separate team to ensure Titan 1 can meet the requirements of the URC. Under him are sub-teams directly responsible for the rotating base and end effectors. The design process could not have been successful without the support of our advisors. Dr. Robson is directly responsible for our team, in charge of ensuring funding and distributing grades to each of our members. Dr. Mayoral and not pictured Jake Bailey play more of the role of coach, gladly volunteering their time to rip apart bad design ideas early. Our underclassmen ensure Titan Rover will be around for years to come. Below are some of our more active underclassmen in the mechanical branch. Be sure to watch out for them in URC 2017.
Hi, my name is Gina Huang and I am the controls lead for Titan Rover. The controls team consists of students from various disciplinaries such as computer science, computer engineering, and electrical engineering. The controls lead oversees all the delegated tasks within the team and specifically works with the computer engineers for the robotic arm control. These members are in charge of software programs. The telemetry lead is in charge of communications within the Rover system and is also responsible of overseeing the electrical engineers. The electrical engineers ensures that the power distribution is maintained. The graduate advisor supports the electrical engineers when assignments are unresolved. William Shockey was the lead systems engineer for Titan 1 for the first half of the year and now is one of the leading advisors in the team. We would like to thank this advisor along with the faculty members, Dr. Childers and Dr. Silverman, for helping the controls team build a strong foundation for Titan 1 and for future generations.
The Titan Mobility System, or TMS, consists of the chassis and suspension under the 433 MHz band. Robustness and modularity were key in the design process to ensure high performance at competition. The chassis is required to house all internal components of the Rover system, as well as act as the base of the robotic arm and the suspension. The chassis was designed to be lightweight and modular to accommodate different arm and suspension configurations. The chassis went through many iterations to become what it is today, a stout platform for the Titan 1 mobility system. The frame of the chassis was fabricated in-house at our machine shop using welded 6061 aluminum channel bar. Acrylic panels line the sides of the chassis to prevent dirt and debris from entering the electronics. Our sponsor Protocase will provide a cover over the top, front, and rear panels to provide strength, fan openings, and an awesome logo on top of the Rover platform. Titan Rover has decided to go with a direct drive system. This decision was made to ensure Titan 1 would be modular to conserve weight in tasks requiring more attachments and reliable due to its resilient construction. The struts of Titan Mobility System have gone through several iterations and analyses and have been designed to endure all forces under the URC within a safety factor of 2.3. The upper struts of the suspension allow for a shock absorber to be translated up and down the entire strut. Testing is underway to find the desirable shock for terrain traversing, and dampers should be implemented before competition. Titan 1's struts attached to the motor and gearbox via hubs, which were water jetted out of 6061 aluminum in-house. these hubs attach to the wheels, which were provided from our sponsor, Wheelies. They are low-pressure balloon tires, capable of driving over multiple types of terrain. Each wheel is powered by its own Turnigy Trackstar motor, driven through a 256-to-1 gearbox. The motor is capable of driving the wheels with enough torque to push Titan 1 through the steep inclines of competition. Each strut of the suspension is capable of being replaced within minutes and allows for the removal of the middle struts during competition for certain tasks. The suspension was fabricated in-house and finished in February. Since then, the suspension has been tested over multiple terrains and tasks and has performed well and is ready for competition.
Hi, my name is Justin Stewart, Telemetry Lead for Titan Rover. Titan 1 utilizes multiple radio bands in order to ensure constant communication with the base station, namely ultra-high and super-high frequency. Within the ultra-high band, two specific frequencies are employed, 433 MHz and 2.4 GHz, while within the super-high band, only the 5 GHz frequency is used. The 433 MHz frequency is used to control the Titan mobility system and the pan and tilt drive camera via a Taranis radio controller connected to an easy UHF transmitter. This setup allows for communication with the drive system consistently up to 4.5 kilometers unobstructed. GPS telemetry data is also received from feedback via a Pixhawk autopilot system over the same frequency, allowing for waypoints to be set. In the unlikely event of a connection loss, the autopilot follows the waypoints back until the connection is reestablished. The 2.4 GHz frequency is used to communicate with the robotic arm via processing and leap motion from the base station control system. Video feedback from a 1 megapixel Moxicam serves as the primary drive camera. Besides the GPS telemetry data, feedback from each of the individual systems is displayed on a web page hosted within the internal network. The 2.4 GHz base station system consists of a long-range router with upgraded omnidirectional antennas, while the Rover system has a signal repeater with the same antennas. The 5 GHz band is solely reserved for the video feedback from the remaining cameras, a Raspberry Pi and a UI XS2 end effector camera. Similar to the 2.4 GHz frequency, the 5 GHz base station and Rover system consists of long-range routers with upgraded antennas to ensure connection over distances of up to 1 kilometer. The purpose of splitting up the systems into separate frequencies ensures that there is sufficient bandwidth to send all the necessary commands and receive all the feedback from the mission-critical systems. It also doubles as a safety net should connection be lost with one of the higher frequencies.
When designing the 2016 robotic arm, both successful and failed design concepts associated with the previous iteration robotic arm were taken into consideration. One major design flaw with the previous model was the lack of yaw control, as well as being rather fragile. The robotic arm needed to be capable of completing dexterous tasks for the URC while remaining easy to control. The 2016 robotic arm has been integrated using 5 degrees of freedom. A standard truss design has been incorporated into the linkages to provide a light and resilient frame. Powered with 3 servos and 2 stepper motors, the arm will have a full 360-degree range of motion from the base and may extend up to 3 feet. The arm is capable of lifting at least 10 pounds, but further testing must occur to test the full capabilities of this rover.
Inverse kinematics is implemented along with leap motion. This allows a huge cutback on the amount of time needed to complete tasks that require the robotic arm. This consists of high-level math based on quaternions and rotational sequences. This mathematical method can create a bigger workspace with little to no singularity and ambiguity. This mathematical algorithm is then translated and programmed into software such as MATLAB, Arduino, and leap motion processing. With the main processing software connected to leap motion sensor, the robotic arm's movements sync with and is based off the infrared sensor operator's hand movements. By utilizing this method of control, the rover can now have one-to-one control as a backup instead of being the main operation. When leap motion and one-to-one controls were compared, completing a task had a time difference of about 75%.